Okay, so hello friends. So today we will discuss the higher order linear differential equations with constant coefficients. So this is the general form of a higher order linear differential equations with constant coefficients. So this is the general form, and for example, this is the examples of how these equations look like. So here you can see two double differentiation of y with respect to with respect to x, then plus 3 single differentiation of y with respect to x, then plus 5y is equal to ex. So this is the fx term, and this is the RH left hand side term. So it can also be written as 2d square y plus 3 dy plus 5y is equal to ex. Why? Because we can actually write d in place of dy dx. Similarly, d square in place of double differentiation with respect to x, and so on. Like triple differentiation, you can write like this: d cube by dx cube, and so on. So here you can see similarly for the second example also, you can replace this with 5 d to the power 4y plus 2d square y plus 7y is equal to x to the power of x. So again, this is our fx function. So this was the general form of the higher order linear differential equations with constant coefficients. So you can see that here the coefficients are constant. So now we will see how to solve these types of equations. So like for example, this is our another like simple form. So here I have replaced the d by dx by d. Similarly, I have used this also. So this equation can be written in this form. So again, I have taken like y as common. So when you bring out y, then you will be left with this polynomial, and I have written this polynomial as fd. So in each type of higher order linear differential equations with constant coefficients, you can actually write the equation in this form, where you can separate out the polynomial function of differentiation, and fd into y is equal to gx, where gx is the right hand side function of x. So now we will understand how to solve these types of questions. So here you can see fd into y is equal to gx. So we know that these are linear equations. So the most important benefit of these linear equations are that you can apply the superposition principles. So now we will apply the superposition principles here. So we have already seen in preliminary classes that how to apply the superposition principle. So at one point you can think of this equation as addition of these two equations. This fd y is equal to 0, where we put the RHS is equal to 0, and the second part is this fd y is equal to gx. So the benefit of this is that this will simplify our calculation. So when you put the RHS as equal to 0, we get complementary part of the solution, and when we take the equation as it is, we are actually finding the particular solution of that equation. So the complementary part of the equation, here we actually see the natural behavior without the involvement of external force, because this gx is like a external force, and this yp, this accounts for the of external inputs or forcing functions. So in this video and upcoming video, we will focus on finding the yc part, that is the complementary part, and afterwards, after 2-3 videos, we will see how to find out the particular solutions. So now here we will discuss the proof of how to find the yc, that is the complementary functions or the complementary part of the solution. So this is our general equation. As you can see here, this is our general equation, and for convenience, I have replaced this in simple terms. Like I have replaced this d with dy dx and so on. So you can see this equation. So this is our equation number 1. So let y1 and y2 be the solutions of this equation, and why we are doing so you will understand after some time. Just for sake, just assume that y1 and y2 are solutions of this equation 1. So this is when you put y1 in our parent equation 1, you will get this equation 2, and when you put y2 in the equation 1, you will get the equation 3. So now we want to check that if y1 and y2 are solutions of equation 1, then y is equal to c1 into y1 plus c2 into y2 is also a solution, where c1 and c2 are constant. So if you want to check this, the best way is to just substitute this in our equation, that is parent equation 1. So when you substitute y is equal to c1 y1 plus c2 y2 in this parent equation 1, then here you can see I have substituted this. So here I have substituted c1 y1 plus c2 y2 in place of y. You can see here. So now what I can do is, now let's rearrange this equation. So you can see that after rearranging this equation, you will find this term. So this will become 0 from using the equation 2, and this second term will also become 0 using the equation 3. So now you can see that overall this will become 0, and it satisfies our parent equation. So now we can say that if y1 and y2 are the solutions of the equation 1, that is the parent equation, then c1 y1 plus c2 y2 is also the solution. And now let's generalize the concept that we have learned. So if y1, y2, y3, similarly yn are solutions of equation 1, then we can say that y is equal to c1 y1 plus c2 y2 plus c3 y3 and so on till cn yn is also the solution of equation 1. And what is the benefit of this, we will see now. Now our main target was to find yc, that is the complementary solution. So our equation was fd into y is equal to 0, where this fd was our polynomial. So now what we can do is, the polynomial part we can express it by factoring it down. So we already know different methods to factor down a polynomial. For example, x square plus 5x plus 6. We know that it can be factored into x plus 3 into x plus 2. Okay. So actually our polynomial in D can be written in factored form. So now basically we are having with our this equation, our parent equation is turned into this equation, that is d minus m1 into d minus m2 and so on till d minus mn into y is equal to 0. Okay, so where m1 m2 and similarly mn are the roots of this polynomial fd. So now let's take a general form, that is this part. Let's equate this is equal to 0, and like we will take every root and equal to and put it equal to 0 to find the solutions. So if you take d minus mn into y equal to 0, so in place of d you can again write as d by dx. So this will become dy by dx because we have to multiply by y also, and this will become minus mn into y is equal to 0. Now you have to just rearrange it, and you have to apply the variable separable method. So just integrate both the sides, and you will finally find that y is equal to e to the power of m n into x. So like we have find one solution, but we have to find other solution also, because there are other possibilities also. So here you can see d in d minus m1, d minus m2, so on, where we have to find solutions for all. Like once we have to equate d minus m1 into y is equal to 0, then you will got the solution y1 is equal to e to the power of m1x. So similarly for d minus m2 into y equal to 0, you will find the solution as y2 is equal to e to the power of m2x. Similarly you can find for like nth term also. So, and we have derived that if y1, y2, y3 so on till yn are the solutions of equation 1, then their addition, that is y1 c1 into y1 plus c2 into y2 plus c3 into y3 so on till cn into yn will also be the solution of the equation 1. So now we will add this. So the finally we will have our solution is y is equal to c1 into e to the power of m1x plus c2 into e to the power of m2x plus c3 into e to the power of m3x plus so on. So here m1, m2 and m3, these are the roots of the polynomial fd is equal to 0. So now we will see some questions of how to find this the complementary parts of this complementary part of the solution of this higher order linear differential equation with the constant coefficients. Okay, so now we will see two simple examples of how to find the complementary solution of the higher order linear differential equation with constant coefficients. So we know that we can write this as d square y plus 5 dy plus 6y is equal to 0. Now let's take out y common. So d square plus 5d plus 6 into y is equal to 0. So now we have to find the roots of this. So let's just equate it to 0. 5d plus 6 equal to 0. So you will see that you will find d plus 3 into d plus 2. You can factor this polynomial. So your roots are d is minus 2 and minus 3. So your solution will be y is equal to c1 and y1 plus c2 y2, and our y1 was what? E to the power of m1x, and y2 was e to the power of m2x. So it will be like y is equal to c1 e to the power of one root is minus 2x plus c2 e to the power of minus 3x. So this will be our solution. So that's how we will implement this. So now let's see one more problem. So you can pause down this video and you can solve this problem. So here again you can see that you can write this as d square y plus dy plus y is equal to 0. So this y will come outside. D square plus d plus 1 is equal to 0. Now let's find the roots of this polynomial fd. So you will, by applying the quadratic equation, you can find the roots as minus of 1 plus minus root b square is 1 minus 4 times of 1, okay, and in denominator you will get 2. So this is a simple like formula that I have used, like ax square plus bx plus c is equal to 0. So we know that the roots are minus b plus minus root b square minus 4ac divided by 2a. So this is not a new thing, that's why I have not discussed in detail. So I have applied this formula, and what roots I get? Minus 1 plus minus 3i, where I is the imaginary function, we are in complex number, is equal to 2. So now what we have to do is, our solution will be y is equal to c1 e to the power, so the first root, that is minus 1 plus 3i by 2 plus c2, and here you will get the second root, e to the power of minus 1 minus 3i by 2. So this is our answer. So actually in future video we will see how to simplify this further, because it can further be simplified, and when you simplify this further you will actually get a better answer. But we don't have to like rush into that part, so we can like understand this till now. So I hope that you have enjoyed this session. So thank you.